never intended to say that. First it takes to do
Can I just interrupt? I'm sorry. We had a request for someone from someone about a hearing loop system. We've organised that. If anybody recognises the email, I've spoken to one person, and that may well be what triggered the activity. Nobody else looking for the hearing loop. That's fine. Thank you.
Good afternoon, everyone. I should first confirm that we are recording this. Yeah? And we are. We're delighted that Mark Priest is giving the presentation today called The History of ENIAC in 3 Programs. Mark's worked as a programmer and lecturer in software engineering and is now an independent researcher and author. And his latest author book, ENIAC in Action, Making and Remaking the Modern Computer, was published earlier this year.
Right, thank you very much for inviting me. I'm delighted to be here. Can you all hear what I'm saying? Good, okay. Well, there's a picture, just to start off with, there's a picture of the ENIAC that we got from the archive. One of the things I want to do in this talk is just show you quite a lot of archival material that we discovered in the course of this project. A lot of which, even though the ENIAC is sometimes described as one of the few things in the history of computing that too much has been written about. When we started looking into the archives in detail, we discovered some astonishing amount of material that didn't seem to be known in the historical record at all, and that really led us to kind of rethink the story that needs to be told about the ENIAC in many ways. So what I want to do is really, as well as sort of tell you the story, is just to show you all the cool stuff that we found in the archive, which hopefully you'll find interesting. My personal interest in it, I'll say a bit more about the project in a minute. My personal interest is as an ex-programmer, and I got into the history of computing at quite a late stage of my career when I went off and did a PhD in science and technology studies in the history of programming in the 40s and 50s. And it surprised me then, and it still surprises me, how little work is done within the history of computing about programming, history of programming languages, software issues, compared with the attention on hardware. Now, I'm aware I'm talking to the Computer Conservation Society here, so I should emphasise I'm in no way denigrating people who are interested in computers and the hardware and technology whatsoever. But I think I would like to see that balance with a greater interest and a greater understanding of the kind of co-evolution of software. Because after all, people built these machines to run programs and ran programs that could run. So the two things are completely interdependent, as this talk will demonstrate. So there's a rather nice picture of the ENIAC, which always reminds me of a kind of American train rushing down the line to the future. It was probably drawn, we don't know who drew it, it was probably one of the engineers in the 1940s, in the middle of the 40s. So the work I'm reporting is really my take on the outcome of this quite extended 3-year project, which resulted in this book, ENIAC in Action. There is a website and a book. I'm such a good salesman, I forgot to bring any copies of the book with me. Now I know at least one person in the audience has got a copy if anyone's desperate to see it in real time today. It's a joint project with Tom Haig and Crispin Rope. I think maybe some of you know or know Crispin. I would like to acknowledge, for my own sake, or the project as a whole, financial support from the Miss Evelyn Rope's Charitable Settlement. it's been going for about 3 years, generated a number of papers, and ultimately this book. But it all started with Christian's interest in a little-known ENIAC program from early 1948, which he wrote a small paper about in the Annals of History of Computing about 10 years ago, I guess, and wanted to basically kind of hire me and Tom, or hire Tom and then hire me, to do the research, more detailed research into the background to this program that he'd discovered. So really, Christian was the instigator of this project. So here's my overview, wittily called program. There is a point to that because the word program is slightly ahistorical when we're talking about the ENIAC. ENIAC did use the ENIAC world. They did use the word program, but they really used it in a different sense. It only began to get its modern meaning around about 1946. So throughout this talk, I'm just going to talk about programs in the modern sense without worrying about being too nitpickingly accurate. And it got its modern sense from this traditional sense where a program with an ME is something that allows you to select a number of things and put them in a certain order, a concept program or a program of studies. So we think that kind of intuitive understanding of what program is what gave the word its modern meaning. And this is a warning I'm going to be using it slightly ahistorically. So we're going to look at 3 programs, and we're going to put an interlude in the moment in the middle to get us. The interlude will be me talking. It's not actually a chance for you to go have a cup of coffee. It's not that. Okay. Maybe not everybody is completely familiar with the ENIAC. I sometimes find it difficult to remember that. But just in case you need introducing to the machine, there's a rather nice photograph of it. So it had 40 panels. This thing from there to that thing there is a panel. There were 40 of these in a big kind of U-shaped room, within which people had desks and worked and came to take advantage of the air conditioning in the Philadelphia summers. So ENIAC was an environment within which you could work and exist. These panels were astonishingly complicated with hundreds of switches, lights, things to plug in, switches to turn, and each of these ones here are accumulators, and they store one 10-digit number. So in some senses it was a very restricted machine, in other senses it was, for the time, certainly astonishingly powerful with electronic speeds, and quite a lot of storage on these function tables. This is a storage device here for read-only storage, which will become important later on. The 2 people in this photograph are Arthur Burks, who wrote the first program I'm going to talk about, and Jean Bartik, who wrote the Betty Jean Jennings, as she was called then, who wrote the second program, or was one of the authors of the second program I'm going to talk about. What are they doing in this picture? It looks like they're actually working. A lot of these ENIAC pictures are painfully staged for publicity photographs. This one looks like they're actually doing something. It looks like Burks is holding a mouse here. There's kind of cable coming out of it. It's not, I'm not going to claim the ENIAC invented the mouse. A nice claim to be able to make. What it was it had a remote control, so you could sit there. What they're probably doing is stepping through a program, one addition, one instruction at a time, not quite an instruction, but they're stepping through a program. What she is doing is probably reading the results of this is the multiplier, the high-speed multiplier. She's probably reading off results, shouting that to him, and he's checking that the thing's working correctly, or he's writing down the results. So basically they're debugging the ENIAC program, and that must have been taken around about 1946, that picture. So that's an image of some people doing programming work on the ENIAC. There's a kind of myth that goes around in some of the secondary literature that ENIAC was built, and then they suddenly discovered themselves in 1945 with a machine that they had no idea how to program, how to make it work, which given what a ludicrous idea it is, it's got quite a lot of mileage in the secondary historical writing. There's no way you spend 3 years building a machine, $500,000 building it, if you don't know how you're going to use it, and you're not fairly confident it's going to be able to work. Programming was always in the plans for ENIAC. Right from the very, very beginning, they were thinking about what they were going to use it for, how they were going to use it, and they kind of wrote, even before it was ready, Program 1 is an example of a program written to have a material effect on the design of the actual machine. So programming was all, right from the very beginning. Programming and the design of the hardware and how it was going to be used for programming went hand in hand in ENIAC's development. Famously, it was ordered for a specific task to calculate ballistic trajectories so they could make firing tables for the guns at the artillery proving ground. John Walkley, the original designer, intentionally designed it to be more general, and really to be able to, I think his vision was basically to be able to solve numerical solutions of linear differential equations. Is what I write. It's a long time since I did the maths. So he had a kind of broad category of useful computations that he had in mind, and it turned out to be much more flexible than that. His original proposals in early 1943 included an outline picture of the machine. So these boxes here represent the different units. There's some accumulators storing numbers, there's a multiplier, something that holds constant data. And inside these boxes are written the kind of variables. He's drawing this diagram to illustrate how a particular computation for this equation down here can be solved on this machine he's designing. And this sketch here, it's not a sketch of the ENIAC, it's a sketch of the bits of ENIAC we would use to solve this particular equation here. And he went on to give a much more detailed, kind of step-by-step account of the individual operations and processes that would be required in solving that equation. So along the top here, we've got the different units of the ENIAC. These are the accumulators, where each one's storing a single number. And then we've got the mathematical notation saying what variable is stored in those accumulators. And then the computation goes stepwise. So down this axis is time. Each of these lines shows you a particular sub-operation, either transferring a number from one place to another, and thereby carrying out an addition, because these are accumulators, not just storage units, or doing multiplication. And down the right-hand side here, it tells you all the details of the operation that's been carried out. So this is a very detailed, this is before the project even be approved, a very detailed plan of how to solve a numerical differential equation using this proposed machine. The project got approved in early 1943, and then the rest of that year they spent sort of designing the basic storage and adding unit the accumulator. Towards the end of 1943, Arthur Burks, who we met on the photograph, made a much more detailed and explicit version of this Maltese program. And partly what they were trying to do was to work out the details of the numbers that ENIAC can store. One of the issues they were first looking at was the numerical analysis aspects of ENIAC. What's going to happen when you start running computation? Up to that point, numerical analysis knew what happened to mathematical errors when you performed maybe 1,000 multiplications. ENIAC was going to perform millions of multiplications. So you have to reinvent numerical analysis to understand what's going to happen with this new form of computation. So they wanted to work out how many accumulators they would need, how many digits they need to store to get the required accuracy, how many program controls, which is a kind of technical ENIAC thing that basically means instruction. How big does the machine have to be to satisfy the people who are paying for it, so that you'll be able to do these computations. So Burks worked through Walkley's program in detail to work out these things, but it also had a kind of side effect, which we'll see in a minute. So this is Arthur Burks' end of 1943. This is program 1. This is a completely detailed program, which in principle you could sort of emulate and run. I haven't tried to do that. And it's, if you remember this diagram, this one is basically a kind of grown-up version. Along the top of the diagram, it's got ENIAC units, all the different 30 or 40 units of the ENIAC, and the computation goes line by line down here. Each line tells you what's happening at a particular stage, what data is being transferred, and there's all sorts of complicated notation on here saying where the decimal point is, because it's a fixed point machine, what kind of shifting you need to do, how many digits of precision there are at various places. It's a completely, with one exception, it's a completely worked out example of how the ENIAC is going to be used to calculate this holistic equation. And he made another splendid diagram, which is basically, this is basically an abstract picture of the ENIAC. So here we've got an actual picture of each of the accumulators. And on the front of it, we've got all the switches and the plugs that were, these are the switches, these are the plugs. And these things here are the buses, the wires that connected to various units. The bottom ones are the control buses, and the top ones are the data buses. This is basically a picture of the ENIAC, an abstract picture of the ENIAC, a diagram, showing how you set it up. So it's summarising all the information about the computation, so that somebody who knew nothing about the maths, an operator, would come along, take this diagram, and set the switches and plug it in and get the program running. And this program, This diagram goes on to somewhere in the Strand, roughly. There's rather a nice letter from one of Berks' assistants in early 1944. Where he says, "Oh yes, I remember we had to make a special drawing table that was 2 yards long to fit these diagrams onto." I should say, if anyone's got any urgent questions as I'm going through, something I've forgotten to mention that you really want to know, then by all means, do what you do. I don't mind answering questions on the fly. So here is, this was a very exciting discovery. This is some notes by John Walkley, whose role in the ENIAC has always been slightly mysterious. And we discovered these notes he made after the early 1944, which is rather nice. But one of the things he's got here is a kind of almost a pseudocode explanation of Berks' program. So Berks' program had 4 distinct steps, and it involved a nested loop. So it's quite a complex program. There's the 4 steps. So you get the 4 steps going to Berks very clearly on this diagram. You can see the nested loop. So B here, it says do 40 cycles of integrate and then print. And the integrate is done 50 times. Okay, so the program that Berks is defining here is a nested loop. It's got an initialization stage, integration and printing, and it does a kind of test run at the end. So after every loop, it did the integration step with no data to check that the machine was still working. So it's kind of built-in checking. How do you control the nested loop? I mean, no one had ever tried to do this before. The only other kind of automated machines at this time were a Harvard Mark I was just by entering into service. And it could do single loops by getting a paper tape and sticking the ends together, so examine memory. The idea of controlling automatically a nested loop at electronic speed was a brand new problem. In his diagram, Berks completely fudged the issue. He just waved his hands and said, "Okay, let's just pretend we've got this device I'm going to call master programmer." In Berks' program, this is a complete black box. Okay? And for a while, we looked at this and said, "Well, okay, yeah, I can see the 4 steps there. So there's the initial conditions, there's the integration step, there's the printing step, there's the check step." And we can see that, an impulse might come in and go out to start the next step and then come back when it's finished. But this 50 and this 40, they obviously correspond to the number of times you want the nested loop to, how does it work? How does that get connected to that? How does that get connected? So if we spent ages looking at this and thinking, what does this notation mean? And it doesn't mean anything. He's just waving his hand. It's like, let's pretend we've got a master program that can do that. So in 1944, the story is Berks is writing this program, and he has to postulate this device to control essentially nested loops in this program. And then in 1944, they've got this new problem of designing this master program, a device which can do that. The original plan, interestingly, was to perform a two-way, to construct a little unit which would perform a two-way branch. Now, with hindsight, you look at this and say, yeah, duh. We know that all you need is an if statement which can sort of choose 2 loops, and out of that structure you can build every other control structure you need. It's kind of obvious to us. But what happens is they did come up with that idea, and they rejected it in favour of something else, which is a really nice example of how things that seem obvious to us in a different historical situation might have been sort of pictured and thought about in completely different ways and very different decisions made. So at the end of 1943, they planned to provide the master program with 30 units which are capable of receiving program pulses on one line and transmitting them on either 2 lines in accordance with pulses received on another line. It sounds rather complicated, but all it means is you've got program pulses coming on a wire that can branch. It's like a railway line that forks at a junction of a railway line, and you've got a switch which you control to make the train go left or right. So the ENIAC is driven by these things called program pulses, which travel along wires from one control to another. So all this is saying is if you have a 2-way branching thing and the pulse is received on another line on the switch, then that's enough to provide all the control you need. Yeah, we know that. This is a very modern perception. There's Mauchly's sketch of one of these things, which he called the difficator. But they didn't do that. They decided to use instead a device called a stepper, which provided a multiple branching. And the thinking here probably was we know what the structure of our computations is. They perform a number of sequences one after the other. So it would be much more convenient from the programming point of view to have a device which can trigger off one sequence, and then another sequence, and then one after that, and then one after that, and then one after that. So the stepper is meant to trigger off a number of sequences one after the other, which is kind of what they wanted to do for this program. And that's a scary electronic diagram there. This is all Walkley, and Walkley designing the master program in early 1944. Two things. So it's a multi-way switch, and it's controlled by an input which moves it on from one output to the next. And crucially, the output, the input, can be derived from the sign of a number. So you can check whether the number is positive or negative. Take the impulse coming from the negative sign of a number. Essentially send the negative sign, convert the negative sign from being a bit of data into a bit of control information, and use it to control the flow of the program, the next thing the program does. So people often, again, this is something else that the secondary literature has got wrong. The idea that ENIAC didn't understand conditional control. At the end of 1943, they had a very clear idea about how to do it using signs, and they built the capability to do that into their new device. They've already built counters. So steppers and counters together to control loops. So here's a stepper. The program pulse comes in, goes out along here, say, it branches out, kicks off this sequence, also triggers a counter. When the counter reaches its top value, 20 in this case, it sends an output pulse which moves the stepper on to the next stage. So there's a nice combination of counters and steppers together here, allow you to control essentially four loops. Four loops is a definite end, which isn't to say that's all it could do. You could also get impulses from somewhere else and move it on without counting. So it's a general purpose control device. Walkley worked out how to use multiple steppers to support nested loops. So here's another nice diagram. Here's a one stepper controlling the main sequence, and here's another little stepper over here controlling a nested loop. So this B output here is repeated 40 times. Within here, the thing is repeated 50 times. So it's the same numbers that Brooks was using in the program. So this is one of my favourite bits of archival material. You can see the rubbing down here, you can see the erasure, you can see Walkley kind of thinking aloud. How am I going to invent this device that will automate the control that we need for Brooks's program? It's really well lovely. So that is essentially Brooks's program done using steppers and counters. So that's program one. So the punchline there is it led to writing the program led to significant unanticipated developments in the design of ENIAC's hardware by inventing this master programming unit. And secondly, ENIAC, after this stage, had the capability of it was computationally complete. Any program that we can write using C++, so they can start with the ENIAC, modulo restrictions of hardware, all the rest of it. It's a totally unfamiliar solution, but it has the same kind of functional capabilities.
Well, what sort of size was the stepper and the counter? How many steps?
The master program ended up with 10 steppers, each of which could control 6 outputs. And the built-in counters on the master program, I've forgotten the total number of maximum loop you could set for one of the steppers. 200 comes to mind, it might be 1,000. Sorry, I can't remember.
Did that number have to be set up sort of
this number here you set up manually on the master program. Yeah, so programming is configuring the ENIAC. Yeah, I should have said that earlier. Yeah. So there's no textual representation of a program here that the machine reads. The humans have a textual representation, and they set up ENIAC. So ENIAC is like at this stage, say carefully, ENIAC is not a universal machine. It's a machine that you reconfigure for different applications. Yeah, so the master program, yes, I should have had the slide here, just to sum this up. The master program ended up having 10 steppers, each of which could branch 6 ways with all sorts of associated counters. And it did with flexibility. So ENIAC was fully automated looping and branching, and in its original form it was used for a number of complex computations throughout 1946, not just ballistic trajectory. In fact, a relatively small number of these computations were to do with its original purpose, because by this time the war was over, and people weren't building actually new guns. They were still building new guns, of course, but not quite as many. So one rather nice example that turned up in the literature is a program in mid-1946 by Douglas Hartree, and this is taken from the write-up in the Royal Society transactions. an application of laminar boundary layer and compressible flow, whatever that means. And he went to visit the ENIAC. They were very worried because the war had finished and all the original people were leaving. And they were worried that the leftover team were going to get a bit depressed that, that's not, the war's over, all the people have gone, this is boring. So they got Hartree over because he was a kind of world-renowned figure in numerical mathematics. You go and use the ENIAC and run some stuff on it. And he did. And he designed his program using these things called master programmer diagrams. So this looks a bit like a flowchart, which I think is no accident. So these things here are representations of the steppers, and inside the boxes you can see how many times each loop is meant to repeat in some of the boxes. These are the individual sequences that make up the program, and the whole thing is linked together in a kind of very flow diagram sort of way. And it's essentially giving you the same information that the flow diagram would give you. So in these steppers you can see this one here is a loop that's meant to repeat 250 times. The ones with no numbers are basically if statements. If you have an impulse coming in here, it will move it on to the next thing without doing any counting. So you can switch between two alternative paths, two alternative control flows, whenever you like. So this is an if statement, this is a for loop essentially. Everything you might need is there. And Hartree also did a setup form, very like the one that Burks did a few years before. These diagrams were used throughout the period that ENIAC was running in its original mode. This is the only one we found, which is actually an original 1946 document. And that's Hartree's handwriting. This must have been before he got valuable help from Kathleen McNulty, because there's actually an interesting error here that suggests it doesn't quite understand what happens when you finish doing a multiplication. So I guess that Hartree kind of, there's an interesting debate, this is a parenthesis, there's an interesting debate, which I'm not going to say anything about today, about the women of the ENIAC and the role of women programmers and the status of programming work. And we've got quite a lot about that in the book. Essentially, we don't quite accept the characterization of the different kinds of work that's sometimes found in secondary literature. I don't want to get into that, I can perhaps talk about that later. But just what seems to have happened here is that Hartree has done this himself, I think, because he had a very detailed knowledge of the ENIAC and how it works. And then later on, he came back and got help, especially from Mr. McNulty, for instruction, advice, helping organising the work for the machine, planning the machine setup for it, and then running the machine. So the historical question, are these people, the famous women of the ENIAC, like Kathleen McNulty, are they programmers or are they operators? And history has tried to recapture them as programmers for obvious contemporary reasons. They were actually hired as operators, and I think people run away from that word slightly because it seems like a kind of low status job compared to a programmer. But actually, in 1946, operator meant a whole range of, it meant being a machine expert, a programming expert, and working in consultation with subject experts who came in to use your machine. So these people, undoubtedly had a crucial role in running the machine and helping people run programs on it. But we think it's a little bit simplistic to say they were the first programmers. Anyway, sometimes we might get into that. Okay, so now we're on the interlude. So this phrase here is, as you will, what happens next is that as a result of his interaction with the ENIAC design team, John von Neumann writes and gets the credit for this first draft of the report on the ENFAC, the document which defines the stored program computer with which we are now all so familiar. As we were carrying out this, we kind of got a bit impatient with the term stored program on the grounds that it wasn't a term used at the time. It didn't come into use until the early 50s. And since then it's been overloaded with so many conflicting and contradictory, confusing meanings that we decided to do away with it. And we wrote a paper saying that stored programming declared harmful or something. I don't think it was called that, but it should be. And we broke down the contribution of this ENFAC report into three different sort of things. The architectural paradigm, the idea that you build a computer having memory and a arithmetic unit and a store and input and output. The so-called von Neumann architecture is one thing. The particular choice of technology, electronics, delay lines, whatever you want to think about, is another thing. And the third thing is the new approach to programming, which we for want of a better phrase, called the modern code paradigm. Paradigm is a nod to Thomas Kuhn's use of the phrase, of course. This, from my point of view, this reflects my sense that one of the really interesting things about this is not so much the design for a new computer, fascinating as that is. That wasn't actually quite so novel in this particular report from mid-1945. What was novel, and what was fairly uncontroversially von Neumann's responsibility, was the design of a new machine code, an operation code he called it, which would allow these new machines to be programmed. So the first draft ENIAC report contains the first modern machine code, saying, and it's completely, it's an old-fashioned version of what's familiar to anyone who's done machine code programming. I don't bother explaining it. In the remainder of this talk, when I talk about the modern code programming, I'm deliberately not saying anything about whether it has to be, whether there's any connection between what you might call a stored program computer, whether it was a stored program. At the time, that phrase wasn't in use, and now I am going to be historically responsible and not use the phrase in discussing machines of the late 1940s. So modern code paradigm is our new analytical term to describe the new type of programming that came along with the ENIAC. Basically what von Neumann did is, I think he took two things. ENIAC had worked out what you needed to be able to automate to run all the programs you wanted to run. If statements, for loops, essentially. He also took the idea of not setting switches and plugging plugs, but coding instructions in the way that the Harvard Mark I machine did and the Bell Lab machines did as punched holes onto the table cards. So we combined those two things and made coding instructions which could express loops, if statements and stuff, which I don't think one should always say with the possible exception of SUSE, I suppose, but I don't think anyone had done that before that stage. And this is the foundation of modern programming. It's got a number of features which are very familiar to us all, of course. Program instructions are stored in addressable locations, so you can refer to an instruction in memory. You can manipulate the program instructions programmatically, and as a result of that, the program complexity is now independent of the hardware. On the ENIAC, on Mark I, you could do certain things, but then we've only got 10 steppers, so we need a program that requires more than 10 if statements, kind of stuff. With the modern code paradigm, there's still a constraint of the size of the memory, but the logical complexity is much freer and less related to particular features of the hardware, and so on and so on. We've got a whole paper about this if you want to know more about this. Having designed this code, von Neumann then tested it by writing a program, which is essentially a sort merge routine where he's supposed to invented merge sort. This is kind of quite well known because Don Knuth wrote an article about it in the 1970s. I don't think anyone's really written anything about it since. And that's just some nice examples of von Neumann's handwriting. The first program that we have preserved from the modern code paradigm. But you can, and again, I could say a lot about this, and I'll try and restrain myself. But he's breaking it down to sequences. So if you read this, I think you can see the reflection, you can see in the way he structures this program, a reflection of his experience in understanding how the ENIAC worked, where you've got a lot of sequences, straight line sequences of instructions, and then you put those together in various ways. So it's completely not spaghetti programming. It's very structured, sequences combined in rigorous, demonstrable sort of ways. And he wrote this program. And in the course of writing it, because it was von Neumann, he kind of wrote it, it's a bit like Mozart, just kind of flew out his head on the paper, I think. He invented this beautiful kind of four-stage programming process in this manuscript. And then in the next couple of years, he got together with Hermann Goldstein and wrote up this programming process in connection with the IAS project. And in 1947, April 1947, April Fool's Day 1947, if I remember correctly, produced this report called Planning and Coding the Problems for an Electronic Computing Instrument. General Principles of Coding and Flow Diagramming. The only new thing in this is the flow diagrams. Everything else is basically what he kind of worked out in 1945 when writing this program. And lest we forget, that's what a flow diagram really looks like. Yes. Interestingly, there are assertion boxes on those flow diagrams, which is quite interesting. Okay, so that's the modern code paradigm. at essentially the same time, March 1947, ENIAC goes to Monte Carlo. So Los Alamos, which of course von Neumann is heavily involved in as a consultant, are interested in blowing things up, either in bombs or in reactors. So they're interested in chain reactions and designing, how to design an atomic core for various purposes. But it's really hard to do this because if you're modelling, you can't model chain reactions analytically. It's just too complicated. There's too many neutrons, and it's all probabilistic, and you just can't do it. So they invented Monte Carlo methods, I'm sure people are familiar with, which is essentially a simulation. You start with what you hope is a statistically representative small set of neutrons, follow their life histories using random numbers to generate where collisions take place, when fission takes place and stuff like this, and then get a whole bunch of statistics which you then analyse. So von Neumann, in collaboration with some of the Los Alamos people, came up with a plan to perform the calculations necessary to do a Monte Carlo simulation of nuclear fusion, it's called, modelling chain reactions in various atomic cores. So this is a little bit from his original, we call it a computation plan. It's the first draft of this thing. We're heading towards program 3 at this point. This is the embryo of program 3 in my talk. So in March 47, you called it a computation plan. It was just a list of computational steps you had to take. Each one basically is a single arithmetic operation, multiplication, subtraction, modelling. And he said it was suitable either for humans or machine computation. At this point, whether he was leaving his options open as to whether it would be done by people with calculators or one of the various more automatic machines, the SSEC or whatever that were around at the time. And what the program does, it uses a lot of punch cards. The details of individual neutrons are punched onto punch cards. You then do a standard sort of Newtonian physics calculation to work out where the neutron is going. Then you generate some random numbers to work out what happens to it, whether it escapes from the simulation or whether it bumps into another neutron. If it bumps into it, whether there's a fission or whatever happens. And then you print out a new card, the updated characteristics of the neutron, and run that cycle over and over and over and over again, thousands and thousands of times, and get a lot of stats about how your chain reaction evolves.
That's a question. Am I right in saying this is actually for the hydrogen bomb? This is for fusion calculations rather than fission calculations?
Yes, I think you are. Whether it's for the bomb or whether it's for reactors, I think you're going to go for
fusion calculations rather than fission.
You obviously know more about nuclear physics than I do. But yeah. But would they be doing calculations for fusion reactors? Because certainly simulations for.
No, 1947, but they were working.
There was certainly the first ENIAC calculation in 1945 was a calculation for Teller's plans for the super. No, for the super, the hydrogen bomb, his follow-on plans. Yeah. Okay, so another aspect of this program is there's an awful lot of data in it. You need nuclear cross-sections, which apparently are basically the probability of what's going to happen to a neutron going through material of a certain kind, how far is it going to get before it bumps into something, stuff like that. For some curious reason they're called cross-sections, but they're essentially a measure of probability. But basically you need a lot of data about the material in your core before you can run any simulations. The actual maths is kind of quite simple. There's a lot of data. All the random, von Neumann originally planned having the random numbers pre-calculated on punch cards and ready to machine. There were plans to set up this computation on the ENIAC. So it is von Neumann writing to Stan Ulam in 47 saying, the computational setup which I sent to you has been investigated more carefully from the ENIAC point of view by HH and AK brackets Mrs. Goldstein. I will probably have a reasonably complete ENIAC setup in a few days. It seems that the setup, as I sent it to you, will exhaust about 80 to 90% of the ENIAC's programming capacity. So they're toying with the idea of running this computation on the ENIAC as an old-style ENIAC setup. And they're doing some, very early on in the process, doing some kind of feasibility tests. But then it all changed. By June, we have von Neumann writing to someone at the Ballistic Research Laboratory saying 4 weeks have passed since I started to discuss with you the new method of setting up and programming the ENIAC. 2 weeks. several variants of this method have now been worked out by Clippinger and his group at Ballistic Research Laboratories on one hand and Goldstein's on the other. And they've tried to, von Neumann and Clippinger have tried to work out how to program with Clippinger's other problems in this new way of programming for the ENIAC. So somewhere between March and June, and we think this was von Neumann's idea, although Clippinger did try to take credit for it later. We think it's von Neumann's idea that you could essentially set up the ENIAC to run the modern code paradigm, which are kind of code that he'd come up with for the ENIAC 2 years previously. He gets the idea of it'd be much easier to use the ENIAC if we set it up to run one of these codes, and all this program would become much easier to do all the plugging and switching.
And then just said in there, you just mentioned the airflow around the shell, so it's not a ballistic trajectory. It's actually this laminar flow with compressed.
Yeah, Clippinger was one of the research mathematicians at the Ballistic Research Laboratory, so they weren't just doing ballistics. They were doing loads and loads of
fits in the artery paper.
Okay, so program 2 is essentially an old-style ENIAC program which acts as an interpreter for an ENFAC style code. Okay, so von Neumann, let me say that again, this is the punchline, this is one of the punchlines. Von Neumann wants to set up the ENIAC to run his kind of ENFAC style code, run a modern style machine code on the ENIAC. So all you need is to set up the ENIAC to run as an interpreter of one of these machine codes. And this is program 2, is how they did this. There were basically kind of 3 versions of it. Adele Goldstein, aka brackets Mrs. Goldstein, produced an initial version in July 1947. Jean Bartik, who we met in the photograph at the beginning, she was now called Jean Bartik by this stage. Rather interestingly, had a programming group of 6. She was in charge of a programming group of 6 people based at the Moore School, University of Pennsylvania in Philadelphia, contracted to work for Clippinger at the Ballistic Research Laboratory, which is quite a nice spin on the women programmers take, because we think this is arguably the first example of contract programming. It's the first time where somebody's actually getting paid, a contract has been written, and somebody's getting paid specifically for writing programs. This is 1947. VRL contracting Jean Bartik and her group to write programs, which is a totally unknown fact before we started this research, but really rather a charming one. So they originally were contracted to write programs for the old style ENIAC, but their work got derailed by these new plans, and one of the first thing they ended up doing was writing a version of this interpreter. And then when they came to run the actual Monte Carlo simulation in early 1948, they made a 3rd version of the program, which then became the kind of final one, which essentially with modifications, and ENIAC ran for the rest of its life. So from 1946, ENIAC ran lots of different programs. In one sense, from 1948 onwards, it only ever ran one program, this interpreter, but obviously for lots of different. So there's a slipperiness about the sense of the use of the word program. There, just because it's cool, is the front page and the summary of Adele Goldstein's 51 order code. It has 51 instructions for technical reasons, which you want to list. Basically, what she worked out was how to superimpose a von Neumann architecture on ENIAC. So some of the accumulators were allocated to the control unit, some were allocated to the arithmetic unit, and some of the other units, and some of the accumulators were just kept as dumb memory. So this, in fact, meant throwing away. Remember, every accumulator in the ENIAC would have numbers as well as store them. If you use some of the accumulators just to store numbers, you're throwing away some of the capability that's been built into the machine, which is an example of how the ENFAC style thing makes, in some ways, makes things simpler. It also, in a way, made the ENIAC more reliable, because there was less stuff you were using, and therefore less stuff to go wrong. The instructions that it was interpreting were stored in a read-only function table, and were executed from a read-write, and then they were copied from there into an accumulator, which is read-write storage, before being executed, which there's no evidence. It raises the possibility that in this version of the interpreter, they could have run self-modifying code, in the sense that at one time, ENIAC could have constructed and executed new instructions, exactly what von Neumann did in his program, and indeed Turing did in his ACE report. So again, this is something that seems very modern to us. Of course you need the capability to have self-modifying code in a small program computer. And they thought of it, and they came up with it, and then decided to do something else. So a bit like the example earlier of the the binary precision things. It's another example of how, what we take for granted in its historical context has actually a completely different story to be told about it than the one that you might have thought was obvious. So the first version of this code had the self-modifying feature, the second version didn't. Gene Bartek's group came up with a thing known as a 60 order code, which used a few additional pieces of hardware and increased the size of the order set to 60 and took away the capability of building instructions. So it used 3 new pieces of hardware. Instructions were decoded directly from the function table, so direct instruction modification is no longer possible. It was a kind of a zero address code. What was on the function tables was just the opcodes, and the addresses were set up in read-writable memory. So they preserved the capability to do address modification, which is precisely the capability that the ENIAC code in 1945 had. So it's kind of very clear. All these details, it's very clear that there were, what they set up on the ENIAC was very, very parallel to the code that von Neumann had planned and designed and specified in the ENIAC report in 1945. And this address modification is important because without that, you'd be really stuck to step through tables and look up things and make loops. So that's program 2. We'll see a bit more of that later on. Program 3 then is the implementation of von Neumann's computation plan to do Monte Carlo simulation. Code it up as a modern code paradigm program, machine code, to run on the ENIAC. And remember, the input and output used was on punch cards. Punch cards are very slow compared to the electronic calculation in ENIAC. So to maximize the computation time, they wanted to make the program more complicated. So every time you read in a card, it did as much processing as possible before you had to do the next punch the next card. Speeding the thing up. And this made the program structure much more complicated. Von Neumann's original plan was a very linear thing with branches. What they actually implemented had loops, nested loops, branches, subroutines, all sorts of things. And essentially, the reason for that is, I think, probably because they wanted to maximise this, maximise the use of electronics and minimise the hit from having slow input and output. And the planning and coding report that I showed you had been issued only a couple of months before, so we begin to design a new program using flow diagrams and the new von Neumann-Goldstein methodology. And the archives have got extraordinarily detailed evidence of the evolution of this program. You can almost follow, you can follow about 10 different stages in the way they designed this program, the way the evolution, the way it evolved. I'll show you some highlights. It started off with an initial flow diagram, complete flow diagram was done by John von Neumann. This is John von Neumann's handwriting. So he did the initial flow diagram for this program. And you can see he's really sticking to his official notation here. There's boxes with meaning scribbles in them, there's symbols, it's very complex, that strange thing with a hash next to it. He's really following his published methodology very, very closely, as you would expect. As the design went along, they evolved data structures and algorithms, and they evolved as the thing went along. So remember, the important thing about this calculation is you need to get these cross sections, the probabilities that tell you what's going to happen to the neutron. And they had to work out, there's a lot of complicated stuff, but they had to work out how best to store and access these data, these numbers, and they came up with some idea about having it's a function of the neutron's velocity, but you can't do a kind of real number to real number function. So they kind of blocked it out and had velocity intervals. Each neutron was in a particular one of 10 velocity intervals, corresponding to each of which there was a cross-section. So you need to do a search. When you've got a neutron, you need to do a search to work out which interval applies and which function value you have to look up. So they use a linear search algorithm for this. And this algorithm, the development of this algorithm goes through a number of stages. And you can see them becoming more familiar with. This is the first time anyone's written a program using a modern code paradigm, using a modern day machine program, except for von Neumann. And they don't know how to do it. How do you design a nested loop with an if statement with a loop in it? No one's ever done that before. And beautifully, in this material, you can see the evolution from this very complicated original version of the algorithm to this kind of intermediate stage, to this final version, where this is a linear search where you're starting in the middle of the array, and then deciding whether to search upwards or search downwards. So it's not going from 1 up to 10. It's start at position 5, and then work out whether to go left or right. So there's a branch and then a loop. And they end up with a nice kind of elegant structure that we would recognise as, a perfectly respectable example of structured programming maybe. But it came from this much more complicated thing. So you can see they're just learning how to program essentially. One of the other highlights is the generation of pseudo-random numbers. They need loads of these. Monte Carlo technique always needs pseudo-random numbers. And again, to speed up the computation, they had ENIAC compute them on the fly. And they had a subroutine, which was called from different program locations to do that. And so, when talking about early programs, people use this, subroutine is one of these words that's kind of very loosely used. So, for example, you might read that Grace Hopper invented a subroutine because she wrote out some code in her notebook that might be useful to copy from the program. Well, yeah, but that's, by a subroutine, what I mean here, following von Neumann, who's apparently, as far as I know, the first user of the term, is something you can call from different locations and return to place in the code from the way you called it. And this program had a subroutine. The only program code we've got from the first version of the program is actually a version of the code for the subroutine. So that is the first pseudo-random number generator, as far as I know, expressed in the code. There's the instructions in the code for the ENIAC. By 1947, they've done a complete flow diagram using a modified version of the official Goldstein von Neumann notation. But much simpler and it's much more like a modern informal use of flow diagrams. You can't really see that, but you get an impression of complexity, which is what we're really after here. It's not a small, simple program, it's a large program with loops, nested loops, if statements. There's the subroutine, so there's the entrance and the exit from the subroutine, away in the box, to the left often itself. And it's called from two places, take my word for it, it's called twice in this program. It'll be clearer on the next question. And that's just to point out that ENIAC was part of a larger computational system using functions. But time is getting shortish, so on. Another wonderful thing we discovered in the archives was the operation log from 1940, well, running from 1947 through to the end of ENIAC's life. And you can, by following this through, you can get their comments on how they actually ran this program, this Monte Carlo simulation for the first time. So, in 25th of March 1948, the machine was being checked preparatory to 60-order code. So up till then, it's been running the program from somebody else in this old style setup. And this Los Alamos Monte Carlo program was the first time they were going to use the EDVAC style code. So here it's been setting it up on March the 25th. March 26th, machine being tested and checked for the AEC Atomic Energy Commission problem. March 29, Nick Metropolis arrives around 4 p.m. and starts getting the background coding on for the AEC. So Metropolis is doing the switching and the plugging to set up the ENIAC to run the interpreter for the style code. 30th of March, Nick got the basic sequence, which is the decode, fetch, execute cycle, and 2 or 3 orders working. So 30th of March, we got first, I think it interprets 2 or 3 orders. Various minor troubles. Next week, continue the process of putting on the background coding, so they're still setting up the interpreter. So people arrive for a demonstration, 4 orders in the basic sequence are working. The machine was demonstrated the first time using a new coding scheme. So 31st of March 1948, the first time that anything approaching a modern code paradigm or a modern machine code program is partially running. First and 2nd of April, something's changed. Nick is now using a 69 order code, not Bartek's 60 order code, but a 79 order code. Some trouble with the function table, this guy Merwin, who's an engineer from Moore School, has come to fix a device called converter. What happened here was that they changed the order code from 60 order code to 79 order code, making use of the device called converter, which essentially was a 1 to 100 decoder and allowed you to free up the master program where it needs. We don't exactly, it's not well documented why they did this. But one of the reasons was to get a bigger order code, so they could optimize the shift instructions. This program had fixed point arithmetic, and you only have 20 accumulators, so each accumulator had lots of bits of data in it. So there's lots of shifting to get individual data fields in and out. Something like 30 or 40% of the operations in this program were shift operations. So it was really crucial that they optimised the shift operations to run as fast as possible. And we think that one of the principal motivations for using this converter and changing the order code was to optimise the shift instructions. But it gave rise to something called 79 order code, but it's a kind of evolutionary improvement of the 60 order code that Bartik's group had worked out in great detail. Testing continues, 12th of April, and now they have enormous problems with the machine at this stage. Demonstration of the machine some or other. Nick is still having trouble with intermittence and has not been able to get the problem running at this time, 12th of April. 15th of April, ENIAC still misbehaving when some debugging is done. ENIAC ready to start problem at lunchtime, and then there was power supply trouble, which delayed things. This goes on for weeks. Spent the day getting details of programming and code and logic of the something straight. The night shift checks through it order by order. So the night shift is debugging the problem at this point. Checking through it by order time is what Burks and Barton were doing in the picture I showed at the very beginning. The night shift are stepping through the program here on the 15th of April. 17th of April is a production run. Finally a good run on Monte Carlo was obtained on the first production run made. 17th of April 1948. Then it all goes pear-shaped again. 2 weeks later, after having trouble getting out all day, Nick returned to 60 kilocycle operation and the machine worked okay. So it officially ran 100 kilocycles. And it couldn't get it working, just endless electronic intermittent problems. And then apparently Nick had this idea of reducing the clock speed to 60 kilocycles, and from then on it worked fine. By using the external oscillator and operating at 60 kilocycles, a good part of the day was spent on productive runs. 29th of April. 1st of May, good day of operation. 10th of May, Monte Carlo problem completed on ENIAC and the machine being checked, ready for the next problem. So between the end of March and the 10th of May, a long, drawn-out process of debugging the code, debugging the machine, getting it running. They have this Monte Carlo program. The ENIAC running an interpreter, and then after that running this Monte Carlo program, 10th of May 1948. Time is, I haven't got, I'm going to carry on, I've only got maybe 10 minutes left, so I've slightly overrun a bit. Not half as much as I could have overrun. I've really got Okay, so here's the controversy then. ENIAC versus the baby. Sounds like a kind of World Wrestling Foundation smackdown match, you know, but, so what we know is that on the 10th of May 1948, ENIAC has successfully, and be very careful with my language here, ENIAC has successfully and repeatedly run a large and complex program written in the modern code paradigm. Okay, unarguably true, I say. On 28th of May, June 1948, of course, the Manchester baby runs a small test program. So this is what got Crispin interested in this project to begin with. He knew the date, obviously knew the date of the baby's first operation. And I found out the date of this program on the ENIAC. It seemed to be earlier, contrary to what, for example, Herman Goldsman gets the date wrong in his book. So Crispin worked out, I don't quite work out how he got this information from, but he found out that this ENIAC had done this thing first. So obviously it's an interesting thing there. Was ENIAC the first program? Well, as I said, I'm carefully not using the stored program phrase, so I'm going to sort of sidestep that one for a moment. And point out that, in a way, there's not really a war around here. The projects were trying to do two completely different things. The Manchester people were trying to build a machine using brand new technology that would demonstrate a particular piece of architecture and get it working. The ENIAC people were trying to get some computation done for lost animals so they could build better bombs. And there's, you know, the projects are so different, so orthogonal than what they're trying to achieve. But it would be, I think, kind of futile to say one did one and the other didn't. They just weren't even in the same race. And so, you know, I'm not saying ENIAC like that. For me, it's not an issue. But I do think you need to be careful about what you say. And for example, here's a quote from the Computer 50 website at Manchester, which says the small-scale experimental machine was the first machine that had all the components now classically regarded as characteristic of the basic computer. Fine. Most importantly, it was the first computer that would store not only data, but any short user program in electronic memory and process it at electronic speed. That last statement is wrong. And one of the major outcomes, the major punchline of this project is that statement is wrong. ENIAC ran the Monte Carlo program at electronic speed. The program was stored in electronic memory and processed at electronic speed. It was a program written in a modern machine code, exactly the same kind of code as the baby ENIAC 8, or not 8, but all the other stored program machines that were being designed at that time. Exactly the same sort of code. And in particular, this is a good note, in particular, Monte Carlo was not a short program, it's about 800 instructions long. It's not, this is the first modern code program run. This is monster, 800 line monster. But they're interested in programming. They're hacking around ENIAC so they can get the program written. They're not trying to push forward the barriers of design here. ENIAC could and the Monte Carlo program did perform address modification. So they had to do various searches to look up values in function tables, and they did that by having the address field of the orders stored in read-write accumulators and modifying that as the program went along. What it couldn't do, because the program operation codes were stored in the read-only function table. So obviously the program couldn't, the ENIAC, even in its reset up version, couldn't have loaded the program, for example. It couldn't have done something like the initial orders, ENIAC. We couldn't change the operation code of the instruction at runtime, but they didn't need to do it for that program, and it's not in the first draft either. But as I mentioned before, Adele Goldstein's first version of this code would have allowed new instructions to be constructed in an accumulator and then executed. But they didn't need that for Los Alamos program, so they threw it away. Their priorities were quite different parameters. On the other hand, the first statement, I think is quite reasonable. The baby was the first machine that had all the components, now classically regarded as a characteristic of the basic computer. Yeah, that's what they were trying to do, and they were the first people to get that running. ENIAC was not a stored program computer, there's no way around it. It didn't have a single unified memory, though when it was set up to run this interpreter, code and data were both held on the function tables in the same uniform read-write memory, a single address space. Read-only address space held both code and data. It didn't have a dedicated arithmetic unit. This was a kind of virtual. What they did with this interpreter was kind of put a virtual von Neumann architecture on top of ENIAC. ENIAC itself is, as it always was, but they put a virtual machine running on top of it. But what they could do, what they were trying to do, what is really interesting about it, is they could run this really complicated modern code paradigm program on the ENIAC. And the lessons I take from that are that we need to dissociate the history of software and programming from the history of hardware. They have separate histories. Programming languages, programs people wrote, why they wrote it, is connected with this kind of, it's like a double helix or something, or a yin yang symbol. The two things go together, but they're quite separate. It's not obvious that the history of hardware is primary. It's also not obvious that the history of software is primary. My interest is more in the program. But it's a balance. And as I said at the very beginning, my motivation for getting involved in this and the whole, really going back 15 years, is that I think the history of software, the history of programming, is really underappreciated in the history of computing generally. So the bottom line is my attempt to produce a witty punchline to summarise this possibly controversial point. Is that you don't need a stored program machine to run a stored program. If you're particularly, if you like the phrase stored program, then it's perfectly reasonable to consider the Monte Carlo program as being a stored program. It is a modern program in all senses. The ENIAC is not a stored program machine, or it's simulating one. So the only possible mention is you don't need a stored program machine to run a stored program. ENIAC ran the first stored program, the baby was the first stored program machine, if you like. So it's, there is a fascinating and largely unknown historical fact here, but it would be really, I think, quite boring to reduce it to an argument about who's first, because it's this different things. Okay, so now that's on the downhill slope to my conclusions now. They ran a second version of the Monte Carlo program at the end of 1948, and it's basically an incremental development of the earlier program. So there's some quotes from the log saying that they started in October and finished it in October. They produced various flow diagrams for this second one, but it's looking much more like there's no attempt to make a nice tidy diagram, they're just hacking away now, scribbling away, lines going all over the place. This is the invention of spaghetti coding in this program. We've got the complete description of the interpreter, the ENIAC setup to interpret this code that we used at that time. We've got a complete description of 60 of the code interpreter. The first complete description of the, well, we have got, this one dates from September 15th September 1948, so that's months before they were running the second version of the Monte Carlo program. So we assume this is more or less the interpreter they were running in October. And we've got the complete code. So there's about 30 pages of this. The first line there is, that second line is the actual order codes, there's mnemonics there, and there's various comments and debugging notes and stuff. It's a complete palimpsest. You can see it in red on this page where they've kind of rewritten some part of it. Things scribbled out. It's like, this is a document. They couldn't print out the code listing. The program is stored on these switches in the app's function table. You can't just print out a listing every time you change a switch. So they seem to have used this document as a kind of working document for an extended period of time, not only to write down the program, but also then to kind of work with it in various ways, including modifications and corrections, and a little extra bit stuck on the bottom there with a different bit of memory. It's a fascinating document. And we spent quite a lot of work as part of this project in documenting this program, because it's sadly we haven't got the complete code for the April version of the program. We have the complete code for the October version. But it's not a brand new thing, it's an evolutionary development. And we did a lot of effort on documenting this program, and there's some various technical reports that you can download from the website. And they include a tidied up version of the flow diagram of the second one from October, which is consistent with the code that we have. So the draft, that flow diagram is not fully consistent with the code. It's much been done. They did the flow diagram, wrote the code, changed the code, didn't update the flow diagram. So we re-engineered the flow diagram, A, to make it readable, and B, to make it consistent with the program. And, it's basically got the same layout as the original one. There's a subroutine, the box all on its own, and there's one subroutine call, and the other one is down here somewhere. Yeah, so two subroutine calls, call and return. But there's no parameters involved in this. So it's not quite. They sadly passed up the opportunity to invent the wheeler jump. They left something for the Brits to invent. We're going to complete tied up, cross-reference, annotated code listening, which anyone wants to get into the nitty-gritty of it. It looks like that. And of course, that's going to refresh. Can you run this program? And for a long time, I thought the answer was probably no. As this project went along, we developed, a complete ENIAC emulator. And this started off as, I just want to understand how ENIAC works, and it's the way things do, took on an effort until I ended up having completed and someone no doubt put me wrong later, but it could be right later. What I've actually done is an emulator or a simulator or a recreation or whatever. We can simulate emulate ENIAC. We've got the complete details of the ENIAC setup for the interpreter from September, and we've got the complete code for the second run, October, which makes it sound teasingly possible that we run it. But what we haven't got is any meaningful physical data. The program has these huge amounts of physical data about cross-sections and probabilities, without which there wouldn't be a lot of point in trying to run it, because you have no idea that what you're doing was any sort of correctness at all. But rather charmingly, on further investigation, it turned out that Clara von Neumann, who's John von Neumann's wife, one of the early women programmers, carried out essentially a dry run of the program, starting at the beginning, going all the way through it, and fully annotating what was going to be in every accumulator at every point in the program, as the program ran. And when the program went off and got some of this physical data from function tables, so you need to look up a cross-section for uranium or something, she wrote in the data, I'm not sure there's an example there, she wrote in the data. So one of the things that this program listing has got is just enough information to reproduce Clara von Neumann's dry run of the program. So of course that made it irresistible. Let me just draw your attention to, I think it's this number here, 1531717035. Remember that? So at this point, we did simulate the dry run, and there's my wonderful user interface of our emulator. You'll see that there, it's the same number. So rather charmingly, having got the emulator, set it up to run the interpreter, put in the code for this program, and then run it with the data that Clara von Neumann provides for her dry run, we get the right answer. Well, she got the right answer. So we're checking what she's checking out. I'm not entirely sure. It's a science fiction times sort of thing going on here. So that's kind of quite cool. Okay, conclusions. So the subtitle of the book is called ENIAC in Action, Making and Remaking the Modern Computer. And I thought a nice way to finish off would just be to explain the subtitle. So making the modern computer. Up till now, in the literature, ENIAC's fame has been this kind of odd, idiosyncratic machine that proved the viability of large-scale electronic computation. People were sceptical that you could get a machine with 18,000 valves to work. The ENIAC project proved that you could, and that opened the door for the production of later, better, proper electronic machines. But what we have discovered, I think, is that, and what I hope to have persuaded you of, it's begun to persuade you of today, is that it's not just about the machine, it's about programming. ENIAC was a central part of it, the ENIAC programming was a central part of the ENIAC project from the very beginning. Remember Mortley's design and his proposal, Wertz's refinement of that was the program which led to the design of the master programmer. And as a result of that, ENIAC fully automated all the crucial elements of what we now know as program control, in particular loops and conditionals in various forms, and the possibility to combine those in various ways of nested loops. All the combinations of control structures that we are familiar with. The ENIAC team kind of understood that you needed them. Their terminology and their notation was different, but they understood what you needed, and they built the ENIAC so that it could support that open-ended complexity of program control. I think it's something that's not really understood. Because of the ENIAC's design, it was limited by certain the physical constraints that limited its programming were different from the physical constraints that limit stored program machines. But in principle, it could do everything. It was computationally complete. It could do everything that we understand as programming. So it's kind of appropriate that the word program began to get its modern sense in about 1945, 1946, just as ENIAC was coming into use. So that's making the modern computer. It made the modern computer in the sense that it demonstrated the viability of electronics, and it came up with an understanding of, a complete understanding of program control, which was new. Remaking the modern computer, ENIAC was a test bed for anything else, modern programming, modern code paradigm, modern machine code, stored programs, whatever you want to call them. ENIAC was a test bed for writing programs in that style. And the documentary evidence is completely clear. The first implementation of such a code was on ENIAC. Perhaps that's the interpreter. And then the first program run in such a code was also on ENIAC. So if by modern computing we mean modern architecture, modern machine code, modern code paradigm, ENIAC is the place where that happened as well. Just probably a place to stop. Thank you very much.
Thank you very much, Mark. As you said, I'm Chris Burton, manager of the project to rebuild the Manchester Baby. You won't be surprised.
would you like to try rebuilding the ENIAC next? I've got the software for you.
You were quite right. There's enough credit to run around for everybody to get a fair share of it. But I have to I have to discuss shortly what we mean by stored program. First of all, the pioneers of the baby computer, when they wrote their definitive paper about it, didn't even refer to it as being a stored program computer. It was the first universal computer machine. And they probably used that expression as a kind of reflection of Turing's view of a universal computer machine. And this particularly included the ability for a program to modify itself. So I think there's two issues about your comparison. I don't think you're comparing like with like. First of all, a program stored on switches, and it's hard pressed to say really that's a stored program. I know it's a program in a fixed place, and I know the program can be changed. But in our modern day and age, when we're talking about electronic equipment, putting it on switches seems to me not quite the same thing as putting it into an electronic memory. And the other one is the question of universality. Has it got all the modern attributes of a modern machine? Because the code wasn't easily modifiable by itself. And so let's say credit is due where credit is there and credit is due, but I don't think it's a fair comparison to think that the baby is claiming everything, but it certainly is claiming originality, universality.
Let's have a conversation with the in the pub, I think. I don't think I disagree with you, really. It would be fascinating to have a more extended conversation that we can have in this particular setting. The phrase stored programming is interesting. I mean, it was first, as far as we know, it was first used in the IBM context in 1949, and they wanted to, I think it was the test assembly, it had its program in two places. One was from cards and one was on a magnetic drum. And the word stored program was introduced as a way of differentiating the program that was on the cards and not stored from the one that was in the machine. So there's no sort of, at its introduction, the phrase stored program has no connotations of program modifiability or any of the things that it's come to have since. It was simply a way of saying a program that was in some way internal to the machine, rather than one that was being read from cards or punch tape in the style of Mark I or Bell Labs. So in that sense, I would say, I would disagree with you to the extent to say that ENIAC's program, it seems perfectly reasonable to say that ENIAC's program was stored in that sense. It was, the fact that it was set up before the program ran is the same as, every program has to get into memory before the program can run somewhere. But the fact that we do that by switches is an aspect of the ENIAC's curious heritage. But I would say the program is stored internally. But to say that, I'm not. In saying that, I'm not trying to sort of piggyback a claim that to say that the ENIAC program was stored. I don't want to claim for it everything that people have associated with the phrase stored program latterly. That was the first point. What else did you say? Sorry. Universality. I'll come back to universality in a moment. As I said, as I was going through, the function tables on which the ENIAC program was stored were read-only. So yes, ENIAC couldn't modify the code of the program it had been set up with. There's no question about that. Neither could the EDVAC as described by John von Neumann in the first draft in 1945. So in that sense, it seems a little bit harsh to criticise ENIAC for not being able to do something that the EDVAC, as proposed in the famous first draft, couldn't do. Which isn't to say that the first draft should be taken as the kind of definitive final statement. So ENIAC's operation codes are not modifiable. Yes, obviously. How important that is to programming, I've come open-minded on that. Not how many examples there are of programs that actually used, in these early days anyway, actually used code modification. I know the Wheeler's initial orders did. If anyone, maybe offline. I'd love to hear more about the examples of actual code modification.
Well, address modification prior to the invention of index registers.
But ENIAC could do address modification. That was my point. Sorry, maybe that slipped by in the myriads of slides. The operational code was stored on the read-only memory. The address field was stored in the read-write accumulators. So ENIAC could modify, to the extent that it could modify the address field of the instructions, the ENIAC interpreter could do that. It just couldn't modify the opcode, and it couldn't change the actual structure of the program in memory. Yeah, but it could modify the address field. Because it needed, for example, to search through the data arrays on the function table by address. So yeah, so it had that capability of program modification. What it could do. Well,
it's more like microcode, basic machine code. It's more like a microcode, it's more like a micro program, microprogram structure. You see it in your interpreter, so it makes it look like a
So when I say ENIAC, there is a slight slippage between the ENIAC itself and the virtual machine that the interpreter puts on top of ENIAC. Yeah, so I think in this conversation, when I say ENIAC, I'm talking about the virtual machine rather than the underlying ENIAC, actually. So not being able to change the operation code, I mean, that means that the ENIAC in its simulation of online architecture wouldn't have been able to do initial orders type setting up of a program in memory. It wouldn't have been able to do a bootloader. Anything that involves putting a program in memory before executing it, it wouldn't have been able to do. Yeah, so in that sense, it's much more restricted than some of the meanings that become associated with the term stored program subsequently. I totally. But it could, crucially, it could do the address modification, without which I don't think we'd be able to, we wouldn't be able to plausibly say this was a modern code program, a modern code paradigm.
Can I ask a question without taking sides, but muddying the waters? So once the stable interpreter was running, did anybody change any of the programs? Or did it get set and get left for months? Of course, then you've got the issue of
the plug patterns of the interpreter or the plug pattern of these?
The hardware, the switches.
The interpreter. So you've got in a sense two programs on ENIAC. You've got the plugging and switching that runs the interpreter. That changed. That kind of evolved. I mean, essentially, they put it on the program, and that's how the ENIAC ran programs for the rest of its life. The program modified, but I don't think they changed it after the program was running. The modern code paradigm program, the Monte Carlo program, being emulated, if you like, on the function, the code set on the function table, could have been changed as the program was executing. But I'm not sure. I don't believe they ever did that. What they did do was have a number of kind of configuration options. So you can see on the this diagram, there are a couple of places where branches like this, rather odd notation here and somewhere else. This refers to two alternative control charts, which are not runtime choice, but a compile time choice, if you like. So before they run a program, they have a whole program set up, and then for a particular run, we come and do a bit of configuration to decide whether it's going to do this block of code or that block of code on this particular run. So there was a certain kind of, I think they're best thought of as compile time options.
Okay. And I guess they did that when they ran the other big applications, like the statistics or did the work forecast.
I guess so. We don't have so much information about which programs, but I would guess so, yeah. But in principle, there's no reason why you couldn't. I mean, I'm not suggesting this makes it for a moment, but in principle, you could, when the program was running, come on and change the switches on the function table to change the program. Some bit that wasn't being run, but that would be madness. That's the sort of thing that Mickey and Goodwin did on Colossus. So definitely that one.
Yeah, two questions for you. Firstly, to remark that when Tony Brooker put his autocode on the Manchester Mark I, there was a hit of something like about 90% of performance. Now, presumably, when you put an interpreter or an ENIAC, there is a performance hit. Do you know what the magnitude of that was?
Less than 10, probably. The fetch execute cycle, the way they call it the basic sequence, when it gets a code, I think it managed to do, so the unit of time in ENIAC is addition time, the time taken to do an addition. And I think when the interpreted code was doing an addition, it took, I think, somewhere between 3 and 5 addition times. And then, so it's that kind of order of magnitude. So not as large as you're suggesting for the
And the second thing was, something came up in discussions with Martin Campbell Kelly a few weeks ago. We were talking about the usage of the word subroutine, which was used earlier.
Yeah.
And he told me something that I should have done years ago and didn't. But subroutine is actually derived from the word routine, which originally meant a program. Routine means a complete program, and the derivation of subroutine from that is obvious. I wonder if you've come across that same notation here in connection with ENIAC.
In connection with ENIAC, I'll talk about this with Martin next time I see him, but this is, so going back to von Neumann's 1945 programme, which he must have written, we don't have an exact date for this, but it must have been after the draft report and before the Eckert and Walkley EDFAC report in September. So summer of 1945, von Neumann makes this sort merge programme. So effectively, it's the merge part of the merge sort routine. And at the end, it's like a 30-page manuscript. At the end of this manuscript, he then has a discussion that says, well, of course, what we want to do is determine the subroutine, using that exact word. And this predates by about 6 months the first use of the word subroutine in the OED, and is earlier than it's the earliest use I've ever come across. But it's not just using the word, it's like my subroutine. What I mean is something where you can, it's obvious if we use it somewhere else, we're going to have to relocate it in memory, so we need mechanisms to adjust all the addresses in the subroutine. And he writes down the program using a parameter for the starting address in memory. And talks a bit about, I think he talks about parameters and return values. So he's, in the space of half a page of manuscript, he's got this really kind of astonishing, well, I think it's former John Warren, he's got this astonishing discussion of, everything you need about subroutines. And he's not specifically, I can't remember off the top of my head if he uses the word routine in the program, but I think that was in fairly wide. It wouldn't surprise me if this was in fairly wide use before that. And that's why he calls it a subroutine. But if we assume that that's the first use of the word subroutine, then it comes ready packaged with a very sophisticated understanding of what you need to implement. The kind of automatic program you need to implement subroutines on a stored program computer, which puts a kind of different spin there. Because traditionally you could say, Hopper had these kind of sort of subroutines, and then they sort of did this and sort of did that, and then David Wheeler does such and such. It doesn't seem to be true. It seems to be this big bang invention of the subroutine.
Maybe it existed before when computers were humans, and people were doing lots of big calculations.
Well, no, people, yeah, but I think we need to be a little bit specific here, because people obviously had subroutines in the sense of bits of instructions that they would need to, would encapsulate particularly useful operations that you need to reuse and do over and over again. With humans, when von Neumann, and this is why when von Neumann uses the specific word subroutine, it is in the context of the stored program architecture where you can rewrite the subroutine before loading the code into memory to rewrite addresses and all this sort of stuff. So it's, I think the idea that you have kind of little bits of reusable instructions in a notebook or in your scheme for a human computer is, I'm sure I have no doubt whatsoever that existed. It's kind of obvious. But I think we shouldn't call it subroutines because, as far as I know, when the term subroutine is introduced, it comes with this very specific technical understanding.
You started your talk by saying we're the Computer Conservation Society, and waving a flag on behalf of software. We, on our committee meeting this morning, were doing exactly the same, making sure that our constitution reflected both the fact that we do hardware and software and systems in general.
Yeah.
And in fact, in some ways, we do more software than hardware. Because with hardware, we don't actually do anything. We just persuade other people to do it. And sponsor them to do it. Whereas with software, we do actually reclaim a bit of software from time to time.
And I do know that. If I gave the impression that I'm not aware of the work being done by the software group, the EO group, and the ENIAC, I was a bit slightly tongue-in-cheek.
Fine.
I think it's absolutely extraordinary that sort of almost before the beginning of computers, they're already inventing emulators.
Yeah.
And as this chap said, in a way it's like a microcode, in a way it's actually more like an emulator to me. So before we've even started thinking about emulating computers now from that era, that first one is a computer. The other thing that I was really struck by was how very similar those first three diagrams you had with the long tram lines, how very similar they were to the diagrams we saw a couple of sessions ago of the
These ones.
no.
But the very long.
No.
Fair old sweater diagram, I think.
That one, no, before, the one before.
That one, yeah.
That one and the previous one, how extraordinarily similar that is to the Babbage.
Yeah, no, exactly, absolutely, yes.
Exactly, that could be exactly the Babbage notation that we saw
To the extent
when you go back another couple where it's got the longer lines going across them.
to such an extent that when I was developing the emulator, the obvious thing to do was the Bernoulli program to run on the ENIAC. The A-levels Bernoulli program set up to run as an ENIAC program. The comparison is so obvious. It almost kind of maps straight onto the ENIAC. And that's actually quite interesting because you're right. They obviously reflect at 100 years distance. Essentially, the fact that the way people understood computation haven't evolved in 100 years. No reason why it should. It worked fine. My take on the people reinventing Babbage or Babbage anticipating why they're so similar is that in both 100 years apart, these people are automating what are essentially existing manual processes of computation in the existing 100 years. They don't change so much. It's not really a great surprise that Mark 1 and the analytical engine are kind of similar. But just to say something a little bit about, just that thing as you reminded me, to go back to these things. I think I'm correct me if I'm wrong, Doran, but I think your group has proved that or argues that the analytical engine as designed couldn't have run Lovelace's Bernoulli program because it doesn't, you can't increment the thing to store the subsequent values in separate locations. ENIAC can do that in a kind of sort of slightly odd way. And this is kind of odd because ENIAC's 20 accumulators are not addressable. I'm talking about the basic 1945 ENIAC, not the emulation, but they're not addressable. You just plug them in. But because you've got these stepper things, you can convert these, you can sort of set up ENIAC so that you've got your own kind of address decoding thing running on these steppers, and you can sort of do all the dynamic data structure programming. You can actually do on ENIAC by making creative use of these steppers, which is again not something that people, not something that's obvious. You can assume because it hasn't got addressability. ENIAC is limited in terms of its computation, but by repurposing some of this technology that they built in, actually you can do more than you thought. Sorry, I was going to pick up your comment on Chris on universality. I'm aware that they described it as being universal. Do you know for sure that they were echoing Turing there? Because it's irresistible to think they were.
No, I don't know that.
Yeah.
But I think it's curious that they did use that term in the title of their paper.
Yeah,
so it was a universal digital computer.
Yeah.
The digital, was modern for them, and it was a computer and so on. No, of course, I don't know. I don't think there's any evidence about that. They weren't particularly hot on the importance of Turing in the building of the baby machine. But they, for example, Kilburn always told me that he went first to the Turing Wilkinson lectures and came away saying, well, I'm not going to build a computer like that. That's the naivety of ignorance of youth, perhaps, I don't know. So it's a little hard to untangle. So I really said, I hope I said, that they used the word universal, perhaps echoing Turing's 36 back then.
Yeah, I've got an awful lot of that. I mean, as far as the ENIAC goes, I would, without sort of getting involved in some of the semantic discussions about what these things might mean, I would say that, off the top of my head, so don't argue with me until we get to the point. I would say off the top of my head that ENIAC was kind of, I don't quite know what Turing complete means, but it could, it had the control capabilities to run all the modern programs, all the control structures, and it could compute, I'm sure ENIAC could compute any partial function for the official definition of Turing completeness is. So it's kind of complete in that sense. I know that's may not be what people mean by universal. In Turing's rather narrow sense of universal, a universal machine for Turing is a machine which can simulate the behaviour of all the other machines. The ENIAC with its, and that's precisely what ENIAC with its following interpreter, my program too, right? That's precisely what ENIAC can do. It can simulate the other behaviour of other ENIAC-like machines. So if I were in the right mood, I think I would argue that ENIAC was, I would certainly mount a defence that ENIAC was universal in Turing's sense, which may not be exactly the sense. I'm not arguing that. I'm agreeing absolutely with the things that ENIAC couldn't do, even in its modified form, the baby and other machines could do. But my view is just fascinating different projects with completely different aims coming together in a sort of grey area in the middle, which has an enormous significance for people looking backwards in time, which I think maybe we can look at more interesting things there, perhaps, with some of the details.
Well, thank you very much indeed for, I can call it a thought-provoking talk, and I hope you find our audience interesting.
Yeah, that's great. Thank you very much.
Oh, good.
Thank you very much for having me.
Oh, thank you
I'm not
very
always
much.
talking, so.
Thank you very much indeed. Now, we're going to have a summer holiday and reconvene on Thursday the 22nd of September here at 2:30 for a talk entitled Crises and Lessons from the History of Software. And this is about that it took little more than 10 years to progress from the first software to the first software crisis, and new crises have been declared in every decade that followed. So the talk is going to explore what lessons have been learned, whether the software development profession has learned the right lessons, and whether there is even a software development profession. And our speaker is Martin Thomas, who's worked in the software industry and with university and government research teams since 1969. He founded Praxis. He's been a partner in Deloitte Consulting with worldwide responsibilities for software engineering and Y2K services. And since 1996, he's worked for himself as a consultant and as an expert witness in major litigation. He's been a director of the Serious Organised Crime Agency, and he's currently a director of the Health and Safety Executive. So details of this are on the website. Please do pre-register for that. And I'd also like to mention again the guided visit to the Ferranti Arga 700 restoration project at RAF Cosford between Shrewsbury and Wolverhampton on Saturday 24th of September. And please do look at our website for details and to pre-register, which will be necessary for that, both because numbers are limited and for security purposes. And all events are advertised on our website, so do look at it from time to time, and you can pre-register from there very easily. And I'd just like to mention that Neville Lyons, who's a relative of Joe Lyons, who's one of the founder of J. Lyons & Co., is going to be giving 2 talks in June at the London Metropolitan Archives in Clerkenwell. And the website is www.leo-computers.org.uk if you might be interested in that. Anyway, all that remains is for me to wish you a very happy summer and to look forward to seeing you again in September. Thank you.
Conversation went in a suitable direction. It doesn't mean you won't bring us to Oxford.